Hello everyone and welcome to lecture 2 in the SE5055 colloid and surface chemistry module. Last time we spoke in some detail about the history of colloids, and we looked at several examples of probably colloids that had been discovered by accident and discussed the notion of the lack of technology being the real inhibition towards discovering the physical chemistry of these systems. Good examples of these were Michael Faraday's red solution of nanoparticles that still can be found at the Royal Institution in London. And we touched briefly upon the industrial importance of these systems. So the idea that these colloidal systems have very significant industrial application and use, whether that be in paints through to the personal care industry. So really, if you were to look at the majority of the sort of chemist workforce of a company like Unilever or Procter & Gamble, you would probably find that a lot of them are colloid scientists. Colloid science also has a very, very wide application in the pharmaceutical industry and in very state-of-the-art modern drug delivery techniques. And hopefully we get time to touch upon some of these towards the end of this module, because there are some fascinating kind of nanotechnological drug delivery techniques that are used currently and have been approved by the relevant European bodies for delivering anti-cancer agents and that kind of thing, and they're all based upon colloidal structures. Another very important application of a colloidal structure in the pharmaceutical industry is in inhalers, which are themselves aerosols. Now, I think that that also highlights something we talked about last time, which is the sheer vast array of different systems that you can have, right? So we're not just talking about emulsions, we're talking about foams, aerosols, sols, and I encourage you to look back at the previous lecture and just become comfortable with the different kinds of systems that we have in colloid science. Now, of course, there's one common theme to all of these, is that it tends to be one phase which is completely insoluble in another phase, but is somehow mixed to form a mixture. And if left alone over some period of time, these two phases would phase separate. And I think the classic example of that is if you imagine that you're at home on a sunny afternoon and you're making a dressing for a salad, for a barbecue, for example, and you mix balsamic vinegar and olive oil. And you mix those two together. One is an aqueous-based substance, the vinegar, and the other is an oil-based substance, the olive oil. When you mix those together, you may whisk them very quickly with a fork, or you may put them in a jar and shake them up. And of course, for a brief period of time, the two substances appear to mix. And indeed they do. But of course, that state is not thermodynamically stable and will very quickly revert back to a phase-separated existence, whereby you likely have a droplet of balsamic vinegar on the bottom and a less dense oil phase on top. We as colloid scientists try to play around with the chemistry of the system in order to promote that stability and stop that kind of phase separation. We also introduced the notion of time in these systems by looking at the diffusion of particles through solution. And we said that we could play around with the chemistry of these systems and either inhibit phase separation by slowing diffusion, We might think about increasing the viscosity of the bulk phase, or indeed increasing the size of the particle. And we said that that can vary for a number of different reasons. But ultimately, that a lot of these particles are trapped in a kinetically stable state, but that state isn't itself necessarily thermodynamically stable. We defined some very basic definitions in colloid and interface science, or colloid and surface science. And we said that when we're thinking about the concentration of a colloidal system, we may not necessarily discuss moles and millimoles. We might talk about weight percent or volume percent. And if we're mixing two insoluble phases, then we expect some kind of area, interfacial area, to be established. When I mix an insoluble particle in water, for example, and I create a dispersion of those particles in water, there is an interfacial area that's associated with the surface of my particle. That interfacial area is the area between the solid particle phase and the water phase. And again, I spoke about this on the last slide, but we also just clarified what we mean by stability in these systems. Now, what I want to do today is consider charge in these systems. We've looked at diffusion, and we've looked at how we can think about a particle moving through solution. But charge plays a very important role in these systems and can be used to modify the chemistry of a colloidal system in order to prolong that period of stability. Now think how important that is in industry, for example. If you have a drug formulation, or if Hellmann's has a mayonnaise formulation, they want to prolong the period over which that formulation is stable, because it can sit on the shelf longer and it saves them money. So a big driver in trying to prolong the stability of these systems, and indeed a big driving force for the colloid scientists in industry, is trying to think about making formulations more stable and increasing their lifetime to ultimately save money. And charge can play a very, very important role in that, and we'll see how charge can play an important role in that as we progress over the next couple of lectures. Today I want to focus on how we can introduce charge into a colloidal system. Now, we know that a particle in suspension will experience some kind of attractive van der Waals interactions, okay, just like molecules do, just like other systems do. And because those particles experience these attractive van der Waals interactions, they will slowly aggregate over time. Of course, this is also dependent on a number of other things, like the viscosity of the solvent and also the size of the particle. But ultimately, those particles want to be together. So, imagine if I have a suspension of carbon black particles in water. Those carbon black particles do not want to be in water. They are hydrophobic materials, which means they don't like water. And over time, they will aggregate due to these attractive forces that operate over quite long ranges in solution between the particles. So what we get is either some kind of reversible or irreversible aggregation, and that depends on the system in question. And we as colloid scientists want to think about ways in which we can stabilize these suspensions, i.e. we can inhibit or dampen these attractive van der Waals forces that exist between particles in solution. So how do we go about doing that? Well, one way to do that is to introduce charge into the system. So have a look at the schematic I show you at the bottom there, which is two negatively charged particles in solution, and surrounding them is an ionic atmosphere of positive charge. Right? It could be sodium ions, it could be potassium ions. There is an inherent attraction between those two particles, but now we've put them in an ionic atmosphere, i.e. we've surrounded them by, in this case, positively charged, let's say, sodium ions. There is now an inherent electrostatic repulsion, because as those two particles move closer together, the ionic cloud, which is dominated by positive charge, will cause those two particles to repel one another. And of course, they won't aggregate. So the key message here is that by introducing charge onto the surface of my particle, I've added an additional interaction component into the system. There are now two forces operating on that particle, an attractive van der Waals force, but also an electrostatic repulsion. And as long as the electrostatic repulsive element outweighs the van der Waals attractive element, those particles will never come together and won't aggregate, and my system will remain stable indefinitely. Now, there are many methods that you can use to introduce charge onto the surface of a particle. Most of them deal with either changing the pH of the environment in which the particle sits. Some use electrolytes, so some might just simply change the ionic atmosphere of the suspension or the solution in which the particle sits. But there are four generic mechanisms of what I call charging particles in suspension, i.e. adding charge to a particle. And I want to just spend the rest of this lecture having a look at those four methods. And in the next lecture, we will sort of discuss the physical chemistry of charge in these systems. So these four generic mechanisms are the ionization of surface groups, ion adsorption, non-symmetric ion dissolution, and isomorphous ion substitution. So number one then, the ionization of surface groups. If you have a particle of the right chemistry, we can charge a particle as a result of ionizing a surface group. And a classic example of particles with the right chemistry here are metal oxides. So iron oxide, titanium oxide, these all form particles in solution. And I'll show you the example of titania here. And here we use pH to control the degree and nature of ionization. So all we're doing is changing the pH of the environment in which the particles sit. And titania is composed of titanium dioxide, and on the surface of the particle there are titanium oxide groups. And you can either protonate or deprotonate those surface groups just by changing the pH. So the isoelectric point of titania is 5.8, which means that at 5.8, that particle is neutral, or the surface of that particle is neutral. I'm talking about charge here. Either side of that isoelectric point at 5.8, we introduce charge onto the surface of the particle. And it depends which way we go, which side of 5.8 we sit, whether it's towards the acidic or the alkaline side, that dictates the charge on our particle. So if we modify the pH to a pH of less than 5.8, so towards the acidic end or the acidic side of the isoelectric point, then we protonate those titanium oxide groups, and you can see that you get TiOH2 plus groups on the surface. And that gives the surface of our particle a positive charge. If we increase the pH towards the basic side of our isoelectric point, so above a pH of 5.8, we deprotonate those groups, and we're left with TiO minus groups on the surface of the particle, and we render the charge of our particle surface negative. So metal oxides and other similar particles are very easy to charge, if you like, and we can do that very simply by just changing the pH. Now, if we have a particle that doesn't have the right chemistry to be ionized, then we can absorb small molecules onto the surface of that particle through other interactions. And a classic example of this are particles of carbon black. These are inherently insoluble in water, right? Particles of carbon do not want to dissolve in water. They're a very hydrophobic material, okay, so they don't like water. But we can add a small molecule to these particles called surfactants. And I just want to briefly look at the generic structure of a surfactant. So you can see that I draw a generic structure of a surfactant. It's a red ball with a blue tail. The blue tail represents normally a straight carbon chain. So just a simple alkyl tail. So just carbon and hydrogen. They're usually quite long, maybe anything between 8 to 14 carbons in length. They're usually pretty straight, and that part of the molecule is hydrophobic. That part doesn't want to be in water. Look at the other region of that molecule then, which is my head group, so the red circle. You can see that this head group is negatively charged. These are usually things like carboxylates or sulfates, and they are hydrophilic, so they like water, they want to be in water. So you can see that there's two very distinct regions of that molecule. One region of the molecule doesn't want to be in water, it's hydrophobic. The other region wants to be in water and it's hydrophilic. Now, we'll look at surfactants in a lot more detail and some of their properties in a few lectures' time, but here I just want to highlight that point, because what happens is when you mix them with a suspension of carbon black particles, those hydrophobic tail groups on the surfactant, through a hydrophobic interaction, adsorb to the surface of those carbon black particles. Now that makes sense because they don't want to be in water and they'd rather be in contact with the hydrophobic carbon black particles. And of course, if you look at the structures on the right, it leaves those hydrophilic head groups pointing towards solution. Now they want to be in water. So what you do there is two things. Number one, you solubilize the carbon black particle, because the outside of the particle is now effectively negatively charged and is happy to be in water. But you also render the surface of the particle negative, which means that it doesn't aggregate. So you completely stabilize the system. Now there is an industrial relevance to this kind of technology. It's the basis of inks, and printing companies like HP and LaserJet, they spend lots of money trying to get the right formulation in terms of the mixture of surfactants that are used to stabilize these carbon black particles. Of course, this is for black ink. And they need a very stable monodispersed liquid suspension to print. And they also need the carbon black particles to spread nicely over the surface of paper. And the surfactants also play a role in this. Now, we can also use a technique called non-symmetric ion dissolution. I give you an example of this here. What we're doing here is we're dissolving unequal amounts of ions and waiting for equilibrium to be obtained. And because we've dissolved unequal amounts, we end up with a charged particle. So a good example of this are the silver halide salts, and they will form particles. The salts themselves, for example, silver iodide, is really not very soluble in water. You can only get about 3 × 10⁻⁷ grams of it per 100 ml. But if you dissolve the silver and iodide ions at unequal concentrations and allow equilibrium to be reached, then you yield a charged silver iodide particle, which is soluble in water because of that charge. If we use an excess of iodide, then we end up with a negatively charged particle, and if we use an excess of silver, then we end up with a positively charged particle. And again, there is some industrial relevance to this, or at least there was some industrial relevance to this, because it was the basis of photographic film technology. Of course, that is completely redundant now, and even the picture of the camera that I show you there is a digital camera. Now, we can also perform something called isomorphous substitution. And here we are replacing one atom within a crystal structure or a crystal lattice by another of a similar size. And a good example of these systems are in clays. Clays are being increasingly used now in sort of personal care chemistry. So any sort of clay-based face masks or moisturizing creams that you have, that come from far-flung parts of the world like New Zealand, are all examples of colloidal clays. They are naturally occurring colloidal particles, and they're about 2 microns or less in size, and they're composed of silica, so silicon dioxide, and alumina, Al2O3 sheets. And you get the packing in the crystal lattice is to have a layer or a sheet of tetrahedral silica, followed by a layer or a sheet of octahedral alumina. The silica, the silicon in the system is tetravalent, and the aluminium is trivalent. If you start to replace either the silicon or the aluminium in the system, then you can yield a charge imbalance. So, for example, you can substitute the tetravalent silicon atom by a trivalent aluminium atom in those tetrahedral layers, or you can substitute one of the trivalent aluminium atoms in the octahedral layers for a divalent cation, so something like magnesium, zinc, or iron. What you do then is you yield some kind of charge imbalance, and you yield a net negative charge in the clay colloidal particle, and of course it's a barrier to aggregation. This does have some industrial relevance. It's used in the production of paper, and it gives a nice gloss on some grades of very fancy paper. And it's also used in things like cosmetics, paint, and medicines. And rather personally there, it's found in face masks. Okay, I'm gonna leave that one there for today. We spoke about the importance of charge in colloidal systems, particularly the importance of how we can increase the stability of a colloidal system by introducing charge, and we spoke about the number of ways that you may introduce charge into a colloidal system. What we will do next time is look at the fundamentals of the physical chemistry of charge in these systems.